Okay, welcome to the afternoon session, Thursday session. This session is about image quality and optical performance, and it is shared by Guillaume and Ilana. I'm just here for 2 minutes. And the reason why I'm standing here is to kind of start with a little bit of chronology and a little bit of history of what happened since LSSTCAM. I know it's only 3 months, but a lot happened, and I wanted to explain from our point of view what happened. 2 minutes. Okay, so first photons. I think you've seen that pictures many, many times. So this is another way of seeing and really giving you the story of what happened that night. So from an image quality point of view, I think that was a very exciting and successful night. And I'm going to go back to the word successful, because I think that's where we have to be a little bit more precise in a lot of our discussions. So we might remember we had a ComCam campaign where we did a lot of telescope alignment, optical testing of the optics. And so we were not completely surprised by the fact that it took us only 3 iterations to have images in focus, and relatively well. So that is, after not quite the third image, but during that night, we got really, really good results for where we were. And I'm going to go back a few times on that. So that, again, that first image was out of focus, but it took us only 2 images to get it to about 1.5 PSF, 45 max across the field, on average across the field of view. And the other point that I wanted to also emphasize is that this was the first time we were using what we call the corner wavefront sensors, and Guillaume is going to go all in the gritty details of what that means. So we had differences between ComCam and LSSTCAM, and it took us a few bugs fixes to actually make it run. Day 2, we spent a lot of time on coordinate systems, which actually turns out to be very tricky, but we actually worked and we closed the loop and we got delivered image quality less than 1 arcsecond PSF. The other thing I want to note on that first night is that we had extremely good seeing. For the first 3 days, we had sub-arcsecond atmosphere seeing, which helped us tremendously too. That didn't quite last. After that, we got more and more into winter and got worse conditions. So then we really worked through getting images for first look. And this is, again, important. First look, we did not necessarily have the goal of sub-arcsecond images. We wanted something that was actually good enough to look good. So we had a goal of 1.2, 1.5 arcsecond PSF, again, with some variation across the field of view. And this is a slide that I kind of tweaked from Keith this morning, if you were at the commissioning session. So again, we said it was a successful first look campaign because we actually got to that level where we could get images that looked good. But that's not the goal and a requirement for the rest of the LSST survey. So again, we went through that step, and as commissioning progresses, so again, for the first point, we actually spend the time mostly at higher elevation. So we didn't have a lot of sag of the optics. We didn't rotate as much. So we really tried to use the system in a very narrow operation environment to make sure we had good image quality. And then as we gone through that, then we started to actually expand the operational range at which we were actually using the system. And that's when we got, things got a little bit more challenging. And this particular session is going to go through a lot of those challenges and where we actually are now that we have passed those first 2 events of first photons and first look. And so that's my second point. We actually went into science validation to really stress out the system and understand what we didn't know, understand in which corner cases the system was not behaving properly. And that's where we are right now. And so we're actually, again, stepping back, thinking about what we're learning from those science validation surveys, and then looking at what can we do in the next 2 months to reach the requirements of image quality and to make sure we take as much data as we can for DP2. And this is very quickly what we're working on. As you can see in this image, we have a statistics on full width of max. Again, this is the mean over the field of view, but you can see we are not uniform. We have a lot of variation top right of our PSF. The central, we do have ellipticity that is not always often meeting requirements. So we're not quite there yet. I guess that's what I'm wanted to say. And we're still in winter. So we actually have worse image quality than if we were in the summer or with ComCam. All right, so that's all for my speech. I'm going to give the floor to Elana, who's going to go through what we include in image quality. And this is really what we want to do in the next 2 sessions, understand where we are, understand what needs to be done and the priority.
Everyone hear me? Yes. Okay, great. Okay, so I'm Ilana Urbach. I'm a commissioning scientist for Rubin, and I'm going to talk about the image quality error budget. I'm hoping that this talk will give an overview of our different sources of image degradation, what's causing them, and kind of lay the groundwork for all of the future talks in these 2 sessions that'll do deep dives into these different sources. So I'll start with a motivation and an overview, and then kind of go into a bit more detail about our different sources of image degradation and our path forward. So I think preaching to the choir here, but optimizing image quality is, of course, a huge win for the survey. When we talk about the full width half max of one of our point sources, this matters a huge amount for everything from flux sensitivity to determining asteroid orbits to deblending superimposed sources. And many of these things, in fact, scale super linearly with improvements. So if we get a factor of 2 improvement, we can get factor of 4 improvements in orbits, et cetera. So what are some of the main ways that images can degrade? Well, first of all, different air temperatures have different indices of refraction. Thus, any horizontal temperature gradients can cause image degradation at any place on the path of the optical path. Also, optics aren't perfect. And of course, if we misalign the telescope, we also introduce degradation. And then, of course, the telescope itself could jitter or shake, or it could not point where it should be pointing, leading to tracking drift. And all of these also cause image degradation. And so to go into a little bit more detail about how each of these impacts are and contributes to our image degradation, first of all, there's atmospheric seeing caused by turbulence in the atmosphere. It is uncorrelated over 3.5 degrees, and thus Rubin will not be able to correct for it. So this is our fundamental limit to seeing. Then inside the dome, there's dome and local seeing caused by temperature gradients in the dome, the mirror, the floor, anything that has a temperature gradient associated with it. Then there's static optics, optical figure error, problems with misalignment and collimation and focus. Then there's dynamic optics. If you have oscillations in the primary support or oscillations in the top end, or say your hexapod is not moving as you expect it to move, that can also cause problems. And then there's the telescope mount, which is generally if the telescope itself is going back and forth, that'll also cause image degradation. And then there's instrument and sensor effects, charge diffusion, sensor flatness, charge transfer inefficiencies, et cetera. So these sources of image degradation approximately add in quadrature. There has a big asterisk, but at least for the purpose of discussing the budget table, this is what we're assuming. So that was the introduction. Now to talk a little bit about the bird's eye view of our delivered image quality thus far. So if we look at our current SV survey and we compare the quartile measurements of our delivered full width half max corrected at zenith to our kind of initial site measurements, site atmospheric seeing measurements, then what we see is a typical excess image degradation caused by our system from all of these sources of image degradation of about 0.9 to 1.1 arc seconds. This is definitely more than we want it to be going forward, but this is where we are in terms of prepping for DP2 for the SV survey at least. However, I will point out that our best images do show excellent image quality. So we know this system is capable of doing much better. So now to break it down a little bit more technically, going into our sources of image degradation and how we're going to measure them. So first of all, for static optics, we measure that with our active optics system, which will be discussed much more in later talks. Our dynamic optics, looking at top end and M1, M3 vibrations, we measure it with accelerometers. Mount motion, we look at, for tracking drift, we have guider measurements, and we can do tracking over longer periods of time to see how we do. For jitter, we have both accelerometers and mount encoders. Then for seeing, for the atmosphere, we have our differential image motion monitor. For dome seeing, we have a bunch of different tools, some of which have been installed, some of which have not been. And then we have our mirror seeing, we have temperature sensors, and also dome seeing monitors here. And then for our instrument, we have done many, many measurements with bench testing at SLAC. We are actually not redoing these measurements now that it's on the TMA, but we have every reason to believe that our bench measurements at SLAC and at the observatory on level 3 are correct, measured at 0.207 arc seconds. And so we're going to use that number going forward. Note that kind of this budget table is looking at kind of median full width half max across the focal plane. Of course, there is variation across the focal plane. We do care about that, and Pierre Francois will give us a talk that includes information about that. So that is also important. But in general, in total, our kind of goal for the survey is 0.4 arc seconds. So now to drill down into each of these a little bit more and talk about which talks we'll discuss each of these. First of all, for atmospheric seeing, we have our differential image motion monitor, which basically looks at light from one star and compares two different light paths from that same star and looks at the differential motion between those two light paths and uses a turbulence model to make an assessment of what the atmospheric seeing is. Currently, our DIM is running, and it mostly correlates with our measured seeing, which is what you'd expect. Sometimes, though, the DIM reports seeing that is significantly higher than what we measure. We have some ideas for why this might be, and we are in the process of studying them. But for right now, for this talk, we have not been using the DIM to understand our overall image quality budget for this reason. But Kevin Fanning's talk will go into this in more detail. Then for static optics, again, we're using the active optics system to try to understand this. So at baseline, kind of optimal temperatures, we see on average about 0.35 arc seconds of static optics contributions as measured by AOS. However, we see clear evidence that when there are temperature differences in the dome, say between the M2 temperature and the ambient temperature in the dome, we see strong excess degradation of the static optics that AOS cannot correct for, that can contribute up to 0.6 arc seconds of excess seeing. And there'll be many more talks in this session devoted to that. Then for mount motion and dynamic optics, so as far as the amount of jitter of the telescope, we see very little jitter based on our mount encoder information, 0.02 arc seconds. We're in process of investigating the hexapod motion. We've also looked at accelerometers. We do not see excess vibrations of our optics. And separately, we're still optimizing the pointing model. So there is still some tracking drift, but we expect to get rid of that. And see Craig Lages and Johnny Esteves's talks in session 2 for more information about this. Then dome and mirror seeing. We do not yet have good direct probes of dome seeing, but the hardware for that has been built. It will be installed within a few months. In the meantime, we're left with sort of proxies for dome seeing. And what we're doing is, if you subtract off the static optic contributions in quadrature from the delivered seeing, then you can see what appears to be potentially up to 0.8 arc seconds of additional seeing. We expect that louver installation and more tests of our EIS control software will help reduce the dome seeing here, but do see Brian Stelter's talks, Jackie Zhang's talk, and Johnny Esteviz's talk in session 2 for much more information here. Also, another big part of our mirror seeing is understanding our M1, M3 thermal control. And this is something where we're finishing the optimization of both the software and the hardware of the M1, M3 thermal system. So we expect to soon have much more improved thermal control. And we even have like temperature sensors within the glass. We expect to have very, very good control of this soon, but it's something that we are still commissioning. So in conclusion, our current understanding of the image quality budget table, I would say there's some uncertainty here, although I think we are coming towards having an understanding of our main sources of image degradation being some combination of our telescope alignment and also our thermal control system. So kind of a summary and next steps, our best images meet system requirements. Most of the remaining image degradation can be explained by dome seeing, mirror seeing, and static optics alignment. And to improve our image quality and our understanding of our image quality, we're going to improve our thermal control system, both our M1, M3 thermal system and our environmental awareness system. We're installing louvers, which will help a lot also with our thermal control. We're performing detailed tests and studies of our DIM, and we're going to continue our optimization of AOS. So I can take some questions.
On Monday, Jelko shown this plot about where we want to be, and the yellow star was at 0.3 of instrument contribution to PSF, but you kind of mentioned 0.4 here. Is the difference contingency, or what are these numbers?
Yeah, so I think our goal is to get to 0.3, I think. Oh, no, sorry, Steve.
I think 0.35 is where you saw. There is a difference.
Yeah.
It may seem like splitting, but it's 0.35. But 0.4 is, is where the SRD minimum is. 0.4 system contribution to delivered image quality.
We would love to beat it, of course, but we can't beat 0.3. I think honestly about it's a little hard because we don't have a reliable DIM, but the question is, what is the best system contribution to image quality that we've seen? And I think it's a little hard to say because we don't have the DIM, but I think we've seen about 0.35.
Yeah, that's a good point, because we want to demonstrate that they're capable to do it, but we got to keep pushing on that to make it more reliable.
That's right. Yeah. Yes. Other questions? Yes, Josh.
I was curious for the site measurement data, if that was at a comparable time of year, or does that matter?
Can I defer? Is there anyone in this room who was on that paper?
I'm not on the paper, but usually when it's historical data and averages, it averages over the year. And remember, we're in winter, and there is definitely worse conditions over the winter. Again, I think we were a lot better with ComCam for that reason.
For folks that aren't paying as much attention to all these details as this team really is, and they really are, I want to emphasize what Brian just said. We have great confidence that what we built is capable of delivering the science that we've been talking about for all this time. What we're concentrating on now is making the nightly operations reliable so that we get that performance over most of the time, right? So it's capable versus reliable, and it is capable. We know that. We've built something that is going to work. We have to now get to the point where it works all the time.
Thanks, Bob. If there are no further questions, Pierre, Francois? Okay, yes.
Oh. Okay. So I am Pierre-François. I'm working as a DM pipeline scientist at Princeton. And I will talk about PSF characterization with the first 2 months of data from LSST-CAM. I will just make a quick rapid note on for a first look event. The PSF was estimated using PSFX, which is not the case of DP1 and what I'm about to talk about, because we are using PIF, and it was done for having fast iteration to make a beautiful image. Okay, so on what I will show in the following, the PSF is modeled using PIF, which is like the PSF model that was used for the dark energy survey. And all the plots I will show in the following, this is estimated using about 3,000 visits. In all the following, I will talk about second moment of PSF, and so about size and ellipticities, and all the information I'm gathering about PSF. This is based on residuals of second moment. And some things that I will focus on is by looking like if we stack PSF residuals across the focal plane, across all the visits, we start to see some features that are characteristic about how we are understanding well the PSF or not. And here, this is like size residuals, first component of ellipticities and second component of ellipticities that I will not talk a lot too much in that talk. I will really focus on size because there is a lot of things going on. And I will make a big zoom on it. So as you can see, like you have a lot of features that are on the focal plane when you stack size of PSF. But I guess there are 3 main patterns. So first, if you look just at ITL sensor, you have kind of a blob patterns. If you look on the edge, there is kind of a ring pattern. And if you look at E2V sensors, you can see like some step function, the small rectangle that correspond to where the amplifier of the CCDs are. It's also on ITL, but because of the blob pattern, it's less clear that it's here. And I will explain what we think it is, because I guess there is a kind of an understanding of what is going on here. And I will focus on each of those features and more. So as you can see, there is these blob patterns, and it was visible also on ComCam, which was also ITL sensor. But the way we got rid of that for DP1, because this is not on DP1, is like by increasing the polynomial order function to interpolate the PSF model. And by switching from order 2 to order 4, you are able to remove most of the features. But at that time, we didn't have a clear understanding of what it was. It was kind of empirical of, I increase the polynomial interpolation. I'm able to get rid of those spatial structure. But now I guess there is a good understanding of what it is. The thing is, like, if you are looking a little bit in a different way, this blob pattern, by doing kind of a zeroth order interpolation, you can see like there is kind of a circle pattern at the ITL sensor level. And if you compare that to the 8 variation of the ITL sensor that was measured at SLAC, you can see there is kind of, they really looks alike. And so the interpretation is like what we are seeing as a blob pattern. This is like the ITL 8 variation, and that is still into the residuals. And so right now, we are trying to include directly those 8 map into the PSF model. And there is some work in progress. Oh yes, it's totally correlated. And there is some work right now going on where we are trying to include that directly into the PSF model. And we start to have some results where we can remove that by including directly the measurement from the lab. But this is still a work in progress. Okay. After, there is a ring pattern. This is likely due to vignetting, but also it might be due to sky subtraction, but I will show that in the following. And then there is like, if you look at E2V sensor, you have like this rectangle pattern I was talking about. And I will go straight to, I mean, it took us a while to understand like what it was. And I guess first real things was thanks to Eli, because Eli, when he was doing photometric calibration, there is like an output of the photometric calibration that is directly the sky background. And if you look both patterns, they really look alike. And if you correlate both, you will see there is a correlation at the amplifier level between the sky background estimated by FGCM and the pattern in the size residuals. And, oh yes. And so to be convinced that this is sky background, you can make a simple test of, if you remove all the faint objects from this plot, those features are basically disappearing. But there is other features that are introduced that I will talk about. But basically, like we are kind of convinced this is sky background that is making this kind of features. And I guess the mechanics, I borrow, I mean, that plot from Alex. This is like, there is a bias when you are measuring a second moment at low signal to noise, and this is amplified by the fact that you have a background. And oh yes, this is something that Eli was suggesting to me, is like when you are doing the instrument signature removal, there is a moment where there is a amplifier offset that is fitted, but that is never applied. And so when you compare the the average at the amplifier level compared to this amplifier offset, there is a total correlation, and it depends on how you are at, I mean, in which filter you are like. But there is a clear correlation between both. So there is some work need to be done on the subtraction of this kind of effect. Okay. And I was mentioning that when I was removing log signal to noise object, you have other features that are appearing into the focal plane. And I guess this is due to what this slide that I'm showing. So if you look at size residuals in terms of flux of the object, there is a clear dependency of size of the PSF and flux. But on that slide, it's not brighter, fatter. It's a brighter, thinner effect. And this is likely due to the fact that brighter, fatter is over-corrected. And so just to be convinced about that, I rerun on CCD number 42, because it's 42, that, I mean, like, I switch off the brighter, fatter correction in red and in blue with the brighter, fatter correction. And you can see that there is an over-correction of it. But we have some ideas about how to move forward about that, and we are working on it right now. Okay, and on another aspect, because I'm speaking about flux, as you may know, like PSF is chromatic because of atmospheric turbulence and differential chromatic refraction. And so here it's not on LSST cam, this is on DP1. And so like if you are looking the size residuals as a function of magnitude, and you make different color beam, you can see like there is a clear like color dependency. And for DP1, you didn't have the loop for correcting for that, but I recently implemented that as a DES year 6 style. And if you are applying that, you are able to take a huge part of this effect. And now this is available. I didn't test that on LSST cam because like there is still photometric calibration happening. Like, so I don't have the color right now for doing that on LSST cam. But it will be here soon. And to finish, something that I found beautiful to look at is like if you look at just the size and ellipticities across the focal plane on a single visit, you can see there is clearly like two different patterns, a smooth gradient that is likely due to the optics varying across the focal plane. But also, I guess this is really clear like in E1 on this visit. You have like stripe patterns that are likely due to the atmosphere. And when you are looking at the residuals, can we see? Yes. I guess you can see that in the residuals, you have like still stripe patterns that are still the atmospheric features. And that is kind of crystal clear why it's happening. It's because like the PSF is still modeled at the CCD level. And so it's not able to get the full spatial correlation. But we are talking about trying to make a full focal plane solution to avoid this kind of things. And I guess I am done.
One of the goals of PIF was to be able to make a model of the PSF over the entire focal plane. Is that happening yet, or is it being done sensor by sensor?
Right now it's done. I mean, it's like DES. It's a sensor per sensor.
Okay,
but yes, the goal is to have like a full focal plane solution. But if you want to do that in the spirit of PIF, you need to have a full measurement of the optical parameters, like to have like all the wavefront reference, Zernike decomposition, and so on. And then you can start to do like to model the atmospheric part on that. But there is like a lot of R&D to be done on that. There is nothing ready right now.
I understand what you're doing is from the point of view of providing a PSF for the science of scientific work with the data. But there's a second use for the PSF, and that is to see the variation in the PSF across the field due to telescope misalignment. By putting all of the wavefront sensors in the corners, we measure only at one radius, while the PSF, of course, measures at all radii. And so the same data that you're producing can also, with some modification, be used to cross-correlate with and to supplement the data from the wavefront sensors. But it might require you're doing some things that you're not doing right now. You're computing second moments, good. That's what we call astigmatism with wavefront sensors. But there's also coma, and that requires third moments. Likewise, there's trefoil, and that also requires third moments.
Yeah, that's that's computed, but I'm not showing. I mean, I'm not showing.
I know that's not your job.
Oh.
You're the people who are calculating the PSF.
So Paul.
No. What I'm saying,
Oh.
I mean, that's computed. All the info is here at this level. But me, I'm trying just to look what is the PSF status, and I guess right now I'm second moment doesn't look as it should be. So there is a little bit before looking at third moment, fourth moment, and stuff like that. I guess there is a lot of information already right here to show oh, we can improve a lot of stuff But I guess what you are saying is also right. I guess when you are trying to do the optical model, when you want to constrain the optics, you are using the second moment and even higher order moment. Maybe Aaron, if you want to talk about what was going on the ES. If I remember, it was not only second moment, but it was second moment and higher order moment to constrain the optical part.
Sure. Thanks, Pierre, Francois. So, in answer to Chris's question and Paul's, right, there is a more detailed PSF estimation. It's in a development branch of PIF, and unfortunately, it was perhaps the development was stymied because the head developer had to do some work on the camera instead. But the goal, right, is to use all of the wavefront information to get a detailed model of the PSF and use that directly. And I think that is still one of the things that the project side is very interested in. And in fact, the work that Pierre-Francois described using the height map is actually very much in that vein, using external measurements to augment the PSF estimation. So I think we are definitely headed in that direction, but at this point, right, we're focused more on second moments than the higher order ones. But to use that full optical approach, what we found in DES is you definitely did need third and fourth order moments. So, and matching them proved actually quite difficult. So I'm really interested to see how well we'll do in Rubin.
Thank Pierre-Francois again.
Can you hear me? All right. So the next presentation will be giving to you by different members of the AOS team. We'll start first talking briefly about just a brief summary of what is the active optic system. In principle, lots of you know about it, but just to put us in the same page. And then we'll move on to talk more through what are our current issues, what are the things we're currently working on, what are the next steps that we have ahead of us. So hopefully that will also give you a vision. And in the same lines as what Sandrine and Ilana were talking, we're trying to bring us all together here and understand what other teams are working on and all the different contributors to the image quality and image degradation. So we'll go ahead and get started. Just to give you a sense of what the active optic system does, It is a system that has two different components, and the main goal of this active optic system is to ensure the images are as sharp as possible. But if you want to be more precise, is to minimize and remove any misalignments and surface errors, deviations or deformations from the mirrors, right? And it does that in two different components. There's a part of these aberrations and these misalignments that are predictable as you move in elevation and as you change the temperature or you move in rotation angle, right? And there's a part of it that's not as easy to predict. So we also have a closed loop, which relies on images that we get from on sky to, we use those images out of focus to estimate what the wavefront is. And once we have the wavefront, we derive what are the corrections on top of those predictable corrections that I was just referring to. And those predictable corrections is what we call the open loop, the lookup table. And so both of those work together in coordination to make sure we deliver the image quality we need to deliver. And more specifically, if you want to look precisely what does the closed loop do, which is one of the main elements, right? It takes out of focus images from the corners of the LSST camera, which are by default out of focus by 1.5 millimeters. And we get intrafocal and extrafocal images. With those intrafocal and extrafocal images, we estimate what the wavefront error is, and then which we do through the wavefront estimation pipeline. And you'll hear from Bryce in a second a lot more about it and what we're working on. And once we have that wavefront error, we derive what are the bending modes and what are the misalignments or corrections on the hexapods that we need to apply. As you may recall, the telescope has multiple degrees of freedom that we have at hand to correct for these optical aberrations. And those include the hexapods in both the camera and the secondary mirror, and also the mirror bending modes, which are the natural way the mirrors have to bend, right? And those are both on the entry mirror and on the primary tertiary mirror, right? So once we have the wavefront error, which is derived with the wavefront estimation pipeline, as I was saying, we derive what are the corrections that we're going to apply. And those are hexapod motions and mirror bending modes, right? And so we'll go into detail, but before we do that, I wanted to give you a little bit of a summary of what's different between ComCam and LSST-Cam. How did our work on ComCam translate to where we are right now, right? As you know, ComCam does not have wavefront sensors in the corner, so does not have any sensor that by default is out of focus. So while we were using ComCam, what we normally would do is we would piston the entire camera intrafocally and extrafocally. And we would do what we would call triplets of images, right? And use those to put the system in focus. So normally when we use ComCam, we did not really have something like a survey as we understand it for LSST-Cam, right? We would get at a specific point in the sky, and we would take multiple sequences of these triplets, and we would put the system in focus at that particular position. But we never really attempted moving as much as the LSST survey will move across the sky and maintain that image quality, right? So it did help us a lot, however, in figuring out a lot of the initial issues and piping the different elements that need to be piped together to get the system up and running. And we were able to put it in focus at a particular position in the sky. Now, with LSST-Cam, and as we start doing the science validation surveys, right, we are moving much more across the different sky. And you'll see in a second that's also part of the reason why so far the images may not look, they don't look as nice as when we're just at a particular position in the sky, right? But that's just to give you a sense that as we went on sky with LSST-Cam, we started commissioning what we call the survey mode, which is the mode in which we take an image at this position, we derive the corrections, and we apply them as we move to the next position and pointing in the sky, right? And as if you recall what I just said, right, that creates more challenges because as you know, there's dependencies in elevation and different variables across this large parameter space that now come into play, and they didn't used to come into play, right? So here, just the performance, a summary performance of how a night looks for us, right? And we normally speak in the language of the telescope, which is in altitude elevation, azimuth, and rotation angle. And also we use what we call the AOS residuals, which are just an illustrative metric, I would say. They do not give you the full picture of how we're doing, but they are intuitively a good way of knowing whether we're doing really poorly or really well, right? Now, that does not encapsulate it all, because as you know, sometimes low AOS residual also show some degradation across the field of view, right? Some gradients, and Josh will talk a little more about that in a second. So here, essentially, this is, I think, the performance over the night of the 8th of July. And you can see there's, on the second row, that's the AOS residuals, and those are pretty constant, although there's some jumps, and the jumps correlate very well. And you see these red lines correlate very well with some jumps in elevation or rotation angle, right? And that points again to what I was saying before, which is one of our main focuses is understanding it, and more than understanding, improving these open loop corrections, those predictable corrections, right? And you can see in the top as well, and there'll be a lot of discussion later in this session about the different seeing measurements that we have, atmospheric seeing measurements, and how those compare. This night was pretty good, but it's just an instance, right? There's other nights in which it's not performing as well, as you all know. And with that, we can move on to start talking a little more about what are the issues and what are the things we're working on, what are our next steps, and let's just dive into them. So I'll start talking about the open loop, which I already referred to many times, but just so you know, normally what we would do to improve these open loop corrections is to do different scans, right? And we try to disentangle the different dependencies, because temperature, elevation, rotation angle, all those come into play, and it's difficult to disentangle, right? Originally, we thought that as we started doing the science verification surveys, we were going to be able to use that data to derive those corrections and be able to refine that lookup table. That proved a little more difficult than rather just doing a sweep at the beginning of the night or at different times of the night at specific temperatures. And that's what we're focused right now. You can see here one of the noisy trends, but there is certainly a trend there on the M2 tilt against elevation that we saw over the last 2 weeks, right? And so currently, I should say as well that our corrections on the open loop component are basically constrained to only rotation angle and elevation, although we would like to include the temperature component, which should be, in principle, one would expect it should be not too difficult to find trends in, but it is also true that there's many different components in the telescope, and the thermal component, like the thermal system, is a complicated system to really understand. And that's why I think Brian will talk more about the EAS and the different sensors that we have. But just briefly to show you some examples. So currently in elevation, what happens is that when we're really low elevations and high elevations, we see degraded performance, and we have some improvements coming from these last 2 weeks that we've been gathering data, and they show very clear dependencies and trends that we have already fitted and we have already deployed to the summit. So we'll see how that improves, but our hope is to repeat that process multiple times until we see that there's, those trends are just flat, and we can ensure at least that, the performance we saw at a specific position on sky as when we had ComCam, we can also show that it's the same across all the surveys that we're taking. And similarly for rotation angle, I just wanted to give you like a brief idea of why is there even a rotation angle lookup table. Well, the camera focal plane is a little tilted. The axis of rotation of the camera is not perfectly aligned with the optical axis of the camera. And then the L1 and L2 lenses are also tilted with respect to the vertex of L3. And all those three components combined make it so that if you rotate a camera, you're also essentially adding a tilt and a decenter on the optical axis. So you need to correct for that. And this plot over here, which we took with some laser tracker data, and actually matches very well some of the findings that Andy Rasmussen had already worked on with ZMAX back at SLAC. And they essentially show how much, as you move in rotation angle, so one end of the on the plot, and the other end of the plot are from minus 90 degrees of rotation angle to 90 degrees of rotation angle. And that shows how much does the camera decenter. And by camera here, I mean how much does the optical axis, that's what we care about, decenter as you rotate, and also how much does it tilt. And so that's the other line over there. And the units, of course, are different from one another, but they're shown here. And so we use the laser tracker to start creating that open loop component, and that worked okay. And then we refined it on Sky, and now I think we believe it's a little better. We believe it's much better than the elevation as of now. But as we improve both, we should see those trends flatten out much more. And with that, I think the last one is just the temperature lookup table that I was referring to before, and just briefly mention that we have noticed that there is certainly some optical aberrations and trends that we see correlated with certain temperature differences. And that points us also to the fact that, just by the focus itself of the telescope changes by temperature. And we've been struggling a little bit to find the right proxy, the right temperature proxy that would show those trends. So we're now in the process of installing new sensors on the telescope as well. And hopefully that will shed some light into those trends, which should be expected. And also some of the improvements that will be discussed in a second on the more of the wavefront estimation and closed loop may also help us tackle some of those. And with that, I think I'll hand it over to Bryce Kalmbach. I realize I forgot to introduce myself, by the way. I'm Guillaume McGee, as I'm a graduate student at Stanford University. And I'll hand it over to Bryce Kalmbach here.
Guillaume's not a grad student anymore, by the way. Hi, I'm Bryce Kalmbach from Slack. I'm going to talk about the wavefront estimation pipeline as part of the closed loop that Guillaume mentioned earlier. And basically, this is the software that's taking us from the donuts on the images through to the wavefront estimates in terms of Zernike polynomials that we put in the butler and then feed into MTOS to get the corrections. So this part of the pipeline is performing well and consistently during the SV across a range of seeing, stellar densities, filters, sky backgrounds. We work in closing the loop in all the filters. And you can see here a very dense stellar background, or a very dense stellar field. And what we have circled here are the donuts we've detected. So the steps of the wavefront estimation pipeline are running ISR on the wavefront images, detecting the donuts, creating catalog, cutting out those donuts, and then running the wavefront estimation algorithms. The algorithms I'm going to show on the next slide. The forward modeling approach that we use is consistently matching the observed donuts and can even handle blending in fields like this. What we do is we've been selecting 4 donuts per wavefront detector. What we do is we rank them by brightness, and then we match the brightest intrafocal and extrafocal donuts and do a joint fit in the wavefront estimation algorithm. And then we take the second brightness and go on down, second brightest and go on down. But it is active research into whether that's the best way to match them up. Should we perhaps maybe match them by how close they are or something other property along the wavefront sensors? So that is the last point there. We're looking into alternative ways to do that. So the wavefront estimation algorithm we've been using is called Danish. It's a forward modeling algorithm written by Josh Myers, who's going to talk next. And what you can see here is we do the joint fit on the intra and extra focal pairs. And the model is doing a good job recreating the donuts that are observed in our wavefront images. And you can see here on the third row that we're even handling when the donuts have blends in the stamps. We're doing a good job with the model matching the observed donut, and the residuals are comparable to the unblended donuts. So the forward model takes into all these effects. And I think Josh is going to say more about the donut blur terms, which handles all the kind of convolution of all the non-optical system effects into the donut. Currently, we're getting about 2 seconds per donut. And I'm going to talk about timing next on how well this is doing. And we have checked this approach and how well the wavefront estimates correlate with match an alternative algorithm called the transportive intensity equation. And they do match very well. So the pipeline timing, where we want to be at is that we take an exposure, get the donut images, then while the next exposure is being taken, we are running the wavefront estimation pipeline, making the calculations, giving those to M2S and getting the corrections back so that the second exposure after that initial exposure, the N+2 exposure, is where we're applying the corrections. To do that, we need to have this whole process done in 31 seconds. We're not quite there yet. So this time that you're seeing here is the time from the close of the shutter to when we're putting the Zernikeys into the butler for MTOS to get. So that's an additional time after this that we need to actually calculate the corrections. We're close. We have a median time of about 35 seconds. About 10 seconds of that is before we even get the wavefront images into our pipeline. So that's image ingestion, everything, and getting the images going into the butler. We run the ISR. That's taking us about 2.7 seconds. We run a very minimal ISR on all the corner sensors. Then we run the donut detection, the cutout of the stamps, and Danish to calculate the Zernikeys in about 9.5 seconds. And then there's still 12 seconds of overhead and IO after that before they're in the butler. So what we're working on now is digging into this overhead and IO, understanding what's in there and how we can beat that down. That's our kind of next step in looking at getting this timing down. Yeah. So you'll also notice that this is a median time. We really need that to be better than the median time. We need all of our visits to be in that time. So there's work to do here. So I'm just going to talk about some issues we've seen recently and how we identify them and what we're doing about them. We've developed a lot of tools to do real-time monitoring. And so the AOS team is often looking at Rubin TV at night. We have a lot of plots to identify when issues are happening. It also, the observing specialists have been using this and identifying things and feeding us information when things do not look right using the tools we put into Rubin TV. So that's how we take a look at how things are going. And when issues crop up, we know where to look and start fixing things. One thing that we're working on right now, so this is some work by Chris Suberlak and John Franklin Crenshaw, is that when we're at the start of the night, when we're in our initial state, sometimes if we're too out of focus, the wavefront estimation pipeline cannot get an initial correction. So we need to do a piston. And so what we did at the start of commissioning was we would look at it manually, measure the donut, come up with the radius of the donut, and feed in a manual distance to piston. We're trying to automate that. And so what you can see here is when you have donuts that are vastly different sizes, that's when the algorithm tends to fall apart. And you can see that we're measuring now automatically a diameter of the donuts on each of the wavefront sensors, and we can use that to send the piston correction and run this automatically. So we've tested on the simulated data that you see here, and it's ready to try very soon on the actual telescope. Another thing that we've been working on is making sure that we get to that full set of 4 donuts per sensor to get the best wavefront estimates possible. Recently, we noticed that in bright sky background, especially in the U filter, we were not identifying all the donuts, even though you can clearly see them by eye. So we've made some changes to our background subtraction and ISR settings and implemented this. And this is on some old data that we tested, and we're actually getting 4 donuts per sensor much more often now. This is actually live on the summit now and was used the other night and has improved the U-band performance. Eventually, what we'll do, hopefully, is move as the pointing model improves, try to use the WCS and just use the reference catalog to do this and cut out that donut detection step entirely, which will save us some time as well. Finally, if you're interested in looking at how we're performing throughout the night, we have developed some Times Square notebooks to do a nightly kind of summary. Or if you just want to dig into the data, you see something on Rubin TV, you want to look at a set of visits, and you can make these plots like the one that Guillaume was showing earlier. We're working on getting more information into ConsDB that will help improve these nightly summaries so that we'll have even more information at the end of every night. And we're working on, and so these have been using the new feature in Times Square to dynamically run these every day. These are being generated automatically. And we have run the data sets at USDF. If you want to actually look at the donuts, we have kind of these aggregate tables that have the Zernikeys for all the visits, have the donut stamps, and you can take a look and if you're interested. So here they are. There's more information at lss.st/campaigns on where all the data is. And that's it. I think Josh is up next.
All right, hello, I'm Josh Myers. I'm a staff scientist at Slack. I'm going to talk about a few other measurements we've been doing and some performance metrics for AOS. So the first thing I wanted to describe is the so-called sensitivity matrix. This is the tool we use to translate the measurements in each of the corners in terms of wavefronts into kind of actionable corrections in the degrees of freedom of the telescope. So you can see, so it's basically a Jacobian matrix, right? It's a derivative. So we actually have good FEA estimates of what this should look like, but it's the thing we can measure on the sky also, right? So we can slew to a field, push on the mirror with a particular bending mode and just see what happens. Is it what we expected? And that's what's being plotted on the figure here. So for example, on the top, you can see the sensitivity matrix data for a particular bending mode number 12 on the primary tertiary mirror. And then the second row is what the finite element analysis tells us the reaction of the system should be. That's a pretty good match. That said, some of the degrees of freedom do have interesting features that we need to, follow up on. We're really interested now in assessing repeatability of this kind of measurement. Does it depend at all on the seeing, for example? And actually, this is a really good data set to understand our wavefront estimate uncertainties also, because we have a pretty solid prediction of what things should look like, so we can compare that against what's actually getting delivered by the pipeline. All right, now so for some performance metrics. I think this was mentioned briefly already, the AOS residual full width half max. This is, the way I like to think of this is we can use the donuts to predict what an in-focus PSF should look like kind of at that position. Because we know what the wavefront error is at that position. You can see that in action in the figure here. So there's this figure comes from a triplet of images. So 2 donuts, 1 intra, 1 extra, and then an in-focus PSF. The blue-green background is the in-focus PSF. The red spots on top are the prediction that come from the analysis of the donuts. So we're doing okay in this example of a very, very bad PSF. But that means if we can make this prediction, then we can measure the full width half max of the red spots and report that this is what we think the contribution of the active optics is for this exposure at this point in the field. So we like to track that. Right now, we've mostly done this by averaging just in the corners. We really need to project into the science area and make this prediction at the science sensors, not for the wavefront sensors. That's work in progress. So right now, this gives us kind of one single number per exposure is what we tend to look at, and it ignores the field of view variation. The next metric I'm going to talk to you about is the donut blur. So Bryce mentioned this a little bit, that as part of our forward model, one of the terms in that forward model is a convolution with a atmospheric-like kernel with a size. And that size, in the best fit of the forward model, is what we call the donut blur. You can see a couple examples here of blurry donuts and less blurry donuts on the bottom. And we actually, the way I interpret this number is it's the full width half contribution from everything except the active optics. It came up yesterday that might be a little controversial, but I'll iron that out with Chuck at some point. So that's a useful metric if you compare it against the actual delivered image quality. Then, the difference there tells you what is the AOS. So we have everything but the AOS. We have the total, so we can figure out the AOS. What's shown on the plot here is the donut blur on the y-axis against the delivered image quality on the x-axis, and then color-coded by that AOS full width half max metric that was on the previous slide. And you can see, we're pretty much on the line, except when we have residuals in the AOS, and then we start moving to worse image quality for a given donut blur. So that's what you expect. And in fact, you can combine those two things, the AOS full width half max residuals with the donut blur, add those in quadrature, and that's actually a pretty good prediction just from the donuts, not looking at the in-focus data at all, of what the full width half max of the in-focus data ends up. So that's pretty powerful. I think it imbues some level of trust in these metrics for the AOS performance. And then this was inspired by conversations just this week, so it's very raw, but I wanted to show you. We do see a lot of full width half max variation in individual exposures. I think probably the most likely explanation of that is active optics. It's hard to get patterns quite like this from just the atmosphere, for example, in the full width half max. So one thing you can try is to take the smallest full width half max you measure on one of the detectors, just assert that there's no AOS contribution at that point in the field. The active optics is working perfectly right there. And then kind of subtract, so that's atmosphere, then charge diffusion, anything that's not kind of AOS controllable, assert that that's uniform across the field, and then that'll tell you what is the AOS contribution, after you subtract in quadrature at every other point in the field. And so I did that for all the exposures on one night, did this subtraction and quadrature of the full width half max and the minimum at some point in the image, and came up with this distribution. And I think this is a reasonable lower bound for AOS performance for this particular night. So, we're somewhere in the 0.4, 0.5-ish arcsecond range. Which is, we want to be better, but that's what the data is. All right, and then finally, we wanted to play for you a movie of the AOS in action for one night. So if you look closely, what should you look for? Or you can see we're kind of raster scanning with the rotator. You might see donuts becoming more and less in focus. You can kind of see them breathe once in a while. That probably means we need a integral gain correction. Needs to be tuned a little bit. You can probably see the donut blur coming in and out. The donuts, that's basically you're watching the atmosphere change throughout the night. You can see when we make a big slew or there's a filter change, it might momentarily, the donuts will change and we'll be out of focus for a little bit, but eventually we recover. So I don't know how. I think we're almost to the end. Yay. All right, one more. Oh, if I can get to it. How do I? All right, yes, so in summary, the AOS is now running, we're operating in kind of science verification survey mode. The expanded range of that mode of observing is presenting us a new challenge. It's Sandrine alluded to at the very beginning. But we're, continuing to plug away at problems. We've improved our donut selection. We've got ideas for improving our wavefront estimation algorithms, looking into repeatability and uncertainties. We've come up with several different ways to characterize the performance in terms of the full width half max that you can directly attribute to AOS. We continue to collect data on the sky. We will improve the lookup tables in both elevation and rotation, study the possibility of doing something based on temperature, and actually primarily just understanding what is the effect of temperature on our system. Yeah, and I think that I said it all. Okay, thanks. Oh, sorry.
Yes.
Okay, great job, everyone on the AOS team. My question is about the temperature lookup table. So can you explain more about what you envision that test looking like? I know for like elevation lookup table, we fix the azimuth and we sweep through elevation. For rotator, we move the rotator angle. We can manually control that, but on a given night, we don't have control over the temperature, at least of the weather. And so is this like a test that would take many nights of observations depending on the temperature conditions? What do you envision that looking like?
I can take a stab at this and then Guillaume can tell me where I'm wrong. I think the goal, this probably would be a slow test, because we can't rapidly change the temperature. There are a few knobs we can change, but there's a long time constant, right? So I think what this would probably look like is spend a significant amount of time, hours, at a fixed at a fixed rotation, and either try to dial some of these knobs that will slowly affect the temperature, or just let natural, the temperature fluctuations over the night happen and watch what happens in that case. How'd I do, Guillaume? Okay.
Hi.
Hey.
There is something that I don't know is like, is there a simulation of the closed loop of like, oh, you have donuts, I'm modifying the mirror, and this is what I get?
Yeah. Part of the TS Web package has a test like that, and there's a whole package for simulating donut images and running them in closed loop and simulation. Of course, the donuts on the real data are much more interesting than the simulated donuts. They have much more interesting effects.
Okay. So I guess I have just a next question.
But we do at least have something. Yeah.
This is like on the simulation, are you able to see the same kind of patterns that are produced by the AOS system on the real data sets when you are trying to close the loop, like of oh, now I'm trying to do like the bending mode of whatever, like, and I still see like gradient of the PSF across the focal plane?
I think all the simulations were a lot easier.
Okay.
Yeah.
So like there is something that is different between the real data and the simulation.
Yeah, there's definitely lots of things in the real data that are not in the simulation. It was very useful for getting up and running and getting all the piping correct. But yeah, we definitely encountered new things on the sky.
So first of all, kudos to the team. Job well done. It's an amazing amount of work you guys have done. So hat tip. So given that we know about the performance with ComCam and how we operated ComCam for the purpose of feeding back into the AOS, have we operated LSST-Cam in the same kind of way where we're using the science area as the wavefront sensor detectors, and then making a comparison of the optical state corrections based on that relative to what we were estimating from the corner wavefront sensor? So I don't know if you've done that yet, you have comments or whatever. So
yeah, so we've taken lots of full array mode data with LSST-Cam, and I think we've even run the closed loop using the full array mode. One thing I don't think we've done is restrict the field of view to just the central raft. So that, right. I think the question is, do we infer a different state when we run in full array mode from the, looking at the center of the field of view compared to when we run in quarter mode, back to back, presumably, right?
Yeah, is there a systematic offset between the corrections you derive from the interior versus the corrections you derive from the corner wavefront sensors? That's the root of, that's the fundamental.
Yeah. Right. I don't think we've done that direct comparison. Tiago wants to say something, but yeah, this is full array, and we do a good job of reproducing the FEA, so that's good. But it's not what you asked. What you asked is, do we infer the same thing in full array mode as corner mode when observed back to back? I think.
Sorry to interrupt. We can't hear anything on Zoom.
necessarily like the closed loop itself wandering off, but like other effects that come into play that make it like jump. And these are like different things, details that we're ironing out that we need to like really look into detail what happened here. And then we realize that a specific thing happened. And I think there'll be some talks later as well, talking about these situations. But certainly these are things that we need to iron out. Yeah.
And I would add, so when it goes funky is often when we change filter or move rotation, but mostly the change filter, right? So that, and then it closes the loop. So the one thing that we also had to do is to really look at the SV survey and then work with the SV survey people to actually constrain the number of changes that happen, because our AOS is not robust yet and reliable yet. It is capable, but not reliable to actually follow all the time. And also we have a lag, as Bryce mentioned, we are not correcting right away. We're correcting at visit n+2 or sometime right now and n+3 or n+4. So it's really hard sometimes to follow up on the SV survey. So we have to really work in collaboration with people. That's explain some wandering off.
Yeah, just to add on that, it's lovely whenever you see one of these issues, whenever whoever's on Sky, to report them, because then we can look at them in detail and figure out what actually happened.
Hey, Zoomies, are you there? Zoomers, where are you? Okay, good.
In the room? In the room? On Zoom? Zoomies?
We can hear you.
Yeah. Are you asking for questions?
Yeah, do you
Yes.
have any questions? Are there any questions on Zoom?
I have kind of a dumb one. Just given the sequence, the amount of time that it takes to, analyze the donuts and calculate the corrections, are you always kind of lagging then? If the telescope is pointed someplace else after the next exposure, are you always playing catch up?
Yes, we are always lagging. The design is we will take exposure n and then apply, do our computation during exposure n+1, and then apply a correction in time for exposure n+2. I think we're maybe not always meeting that design goal currently, but that is the design. In addition, if we ever make a large slew, then we kind of reset and start it over again with the corrections.
Okay, thanks. So the images with the worst PSFs are the ones after slews? I mean, can you see a sequence of improvement?
Yeah, we've definitely seen ill effects after large slews or filter changes, things like that. Yeah. Yeah.
Yeah, so this is Craig. I have a question. So
So it would seem to imply that those big jumps say that the lookup tables still aren't as good as they could be. So those should get better as the lookup tables improve. Is that true?
I think they should get better. You know, maybe, you know, we always expect there to be a need for the closed loop on top of the lookup table, but yeah, we will improve the lookup table, and I do think those jumps should improve.
Thank you all for attending. Now we'll have the other session in 30 minutes.